In this video, we're going to talk about analysis of variance. Thus far in the course, we've examined a couple different ways that you can compare the means of two groups or two populations. If the samples that are drawn from the populations are dependent, you can compare the two means via a dependent t-test. If the samples that are drawn from the populations are independent, then you can compare the two means or the two means of the populations or the two groups via an independent t-test. But what do you do if you have more than two groups, if you have 3 or 4 groups? That's where analysis of variance comes in, and specifically what we're going to do in our course, which is one-way analysis of variance. Here's a problem from our text. To shorten the time it takes a student to make his favorite pizza, the student designed an experiment to test the effect of sugar and milk on the activation times for baking yeast. Specifically, he tested 4 different recipes and measured how many seconds it took for the same amount of dough to rise to the top of a bowl. He randomized the order of the recipes and replicated each experiment 4 times. So he ran a number of trials with each type of recipe, recorded the activation time for each recipe. Note that activation times are quantitative variables, so we're going to be comparing quantitative data, which we do via means. The task to complete for this problem: state the hypotheses about the recipes, both numerically and in words. Assuming that the assumptions for inference are satisfied, perform the hypothesis test and state conclusions. And then, would it be appropriate to study multiple comparisons? We'll address the first 2 in this first video. Then I'll have a follow-up video which will talk about multiple comparisons. So let's focus on the first one. State the hypotheses about the recipes, both numerically and in words. What the student has done is developed 4 different recipes, combinations of sugar and milk, mixed them with yeast, and determined the amount of time it takes for each recipe for the yeast to be activated. The null hypothesis is always, the skeptic's hypothesis, that the mean activation time for the 4 recipes is the same. And that would be, in words, the hypotheses. Now, the alternative hypothesis is not that all 4 activation times are different, but at least one of the activation times is different than the others. It might be that all of them are different. It might be that 3 of them are the same and one's a whole lot more or one's a whole lot less. It might be that 2 are greater than others and 2 are less than the others. All we know for the alternative is that there's some difference among the population means. Numerically, you could write this as, and I think it's more symbolically rather than numerically, that mean for recipe 1 equals mean for recipe 2 equals mean for recipe 3 equals mean for recipe 4. And I would prefer for the alternative, just to continue to write the alternative in words, that the mean activation time for at least one of the recipes differs from the others. Now, what I've got to do is examine, so how do we do that? How do we do that statistically? So what I've done is I've come up with essentially 2 different scenarios. If the null hypothesis is true, then the population means, the activation times for the 4 groups are about equal. Now here's 3. I just did that for simplicity, but just so you'll see. Okay, so here the top is the null hypothesis being true, and the bottom is that 2 of the activation times would be the same and 1 would be different than the others. So let's take a look at how these are different. Statistically, we do that with what's called an F ratio. The F ratio is the ratio or the fraction of the variation between groups over the variation within groups. On the formula sheet that we use, it says mean MST over MSE, which stands for mean squared of the treatment over mean squared error. Let's sort of talk conceptually about what these are. For the F ratio, you've got, first of all, I'll look at the bottom portion, the variation within groups. Basically, that is a measure of the variation, the standard deviation, or the spread of each population. So the blue population is a spread from about here to here. For the red is a spread about here to here. Essentially, the spreads of the 3 of them are about the same. Notice that this is true whether the population means are equal or the population means are different. What we're doing is we're going to take the variation, the spread of the black distribution, the spread of the red distribution, the spread of the blue distribution, and basically average them. So we get an average of the spread within each group. Notice that for the top, That would be a certain value. The spreads are all about the same, so the averages will be about the same. On the bottom, it doesn't matter where the distributions are. The spread of the blue on the bottom is the same as the spread of the blue on the top. So the variation within groups is just an average of the variation within each of the groups. Okay? The variation between groups looks at each group and says if basically what is its variation with respect to the overall mean. So the overall mean of all of the data, if I put all the data together, the overall mean might be about in here. So I take the black distribution and say, well, that's how far is that from the overall mean, multiply that by the number of cases I have, so I get a variation there. Do it for the red, do it for the blue. Notice that these are relatively all fairly close to the overall mean. Notice what happens, however, when one of the populations is a whole lot more or a whole lot less than the other. In this case, it's blue is the mean is greater than the others. The overall mean would be up a little bit, but basically if you look at the variation, how far each of these means is, each of these groups is from the overall mean might be about where my cursor is. So the variation, the spread in the bottom scenario is a whole lot more than the spread in the top scenario. Now how that plays out is the top scenario, if the groups are all about the same, okay, the numerator of my fraction would be about the same as the denominator. So the F ratio is about 1 when the populations are the same. However, when at least one of the populations is different, well, remember the denominator stays the same. It's still going to be the same as whether the means are, or whether the groups are together or not. But the top is going to get a whole lot bigger. So when the groups are equal, you should get an F ratio of about 1. When the groups are not equal, this F ratio, the numerator will get bigger and bigger and bigger. The F ratio will get bigger. So it might be 3, it might be 4, sometimes 24. In other words, the greater you get from 1, the more sure we are that at least one of the groups is different. Okay, so let's go down to back to the problem. Part 2 of that problem. Okay, we've already talked about part 1. Part 2 said assuming the assumptions for inference are satisfied. So let's talk a little bit about those. Basically, the assumptions are that you have to have independent random samples, that all of the populations are normal, and that the spread of the populations, the standard deviation of population 1 equals the population 2, is approximately, all of the spreads of the populations are about the same, and they're unknown. So basically you could see here, regardless of what we have, each of these would satisfy the assumptions. The populations are all about normal. The spread of each population, basically the standard deviation of the spread of the distributions, are about the same. And let's see, what was the third one? The populations are normal, the spreads are the same, and the samples are independent. So basically stated in terms of the problem, we've got independent random samples of activation times. For each recipe, the distribution of activation times for all trials, not just for the 4 that we observe, but for all trials is normal. And again, the way you test that is you would probably have to construct a histogram. We're not going to do that in the 205 course unless I give you the histogram. And then thirdly, for each recipe, the standard deviation of activation times, not on just the 4 trials we looked at, but on all trials, are approximately equal. All right. Now, you can also see this. The problem gives you the box plots of the data. So for the 4 recipes, here's recipe A, B, C, and D. These are the box plots of activation times. You can check the assumptions via box plots. You say, okay, well, basically each of these box plots is relatively symmetric. The C is a little bit less so, but it's not dramatic. It's not like there's a big long spread on one side versus the other. So the distribution of the activation times are approximately normal. Just like you check for histograms, it's not going to be exact. The standard deviation time, the spread of each of these, is basically about the same. Not, basically one is not, one of these spreads is not like 400 versus the other about 200. In each case, these are between 100 and 200, so they're relatively the same. Okay, so let's do that. Let's conduct the test. So assuming the assumptions are satisfied, perform the test. Like all hypothesis tests, we have to have a null hypothesis, which we stated that the mean activation times for the 4 recipes is the same. The alternative is that the mean activation times for at least one of the recipes is different. The F ratio is our test statistic, and that would be, you could write it as the variation between groups over the variation within groups, or in shorthand from the formula sheet, MST over MSE, mean squared treatment over mean squared error. And lastly, a decision rule. We're going to reject H0 if the p-value is less than some alpha that's given, the level of significance. And remember, the p-value here would say, basically, if the mean activation times, if the null hypothesis is true, then how likely is it that we would see the F ratio, which would be basically a ratio that examines the variation between groups over variation within groups, how likely is it that we would see this particular F ratio? Okay, to do that, we need to go to StatCrunch. So what I've done here is I have got the data pulled up. Under Stat, you go to Anova, and it's a one-way Anova, which is all we're going to do in this course. And click one way. Now, notice here, if I look at the data, all of the data is in one column. So I'm going to go down to values in a single column. The responses are the data we're looking at. We're looking at activation times. The factors are the groups. We're looking at different recipes for the groups. And then I'm going to compute. Oh, there we go. And we get some data. We get the results from Anova. And what I've done is I've pulled that up on another slide so we can take a look. So here's what you'd see with Anova. So you've got basically the responses. This is the sample data. Notice again the standard deviation, the spreads of the samples are about the same. Okay, that's what we were hoping in our assumptions. The mean squared recipe, mean squared treatment is about, what is this, 212,000, it's quite large. The mean squared treatment is only 4,700. When we take the ratio of those two, we get an F statistic of about 44, a little bit more than 44. Now, as you can see, that's significantly greater than 1. Okay, so if the groups are truly equal, the likelihood of seeing an F ratio of 44 is less than 0.0001. In other words, this is very rare to find if the means of the groups are truly equal. So just like we've done with the other hypothesis test, we'd say since the p-value, which is less than 0.0001, is less than 0.05, we're going to reject H0. If we reject H0, we conclude, as you go back to the alternative, we're going to accept the HA. So we're going to conclude that the mean activation time for at least one of the recipes is different than the others. And that's the hypothesis test. The last part of this, the problem says, would it be appropriate to follow up this study with multiple comparisons to see which recipes differ in their mean activation times? So going back to our conclusion, we conclude that at least one of the activation times on average is different than the others, but we don't know which one's different. To determine which of these 4 groups is different, which has a greater mean time, which has a less mean time. Keep in mind, these are just the samples, so the sample, you can't determine necessarily which groups are different from the samples. We're going to do the statistics to determine, based upon these samples, which of the overall activation times for all trials of recipe A's, B, C, and D, which ones are different. But going back to the problem says, would it be appropriate to follow up with multiple comparisons? Since we rejected the null hypothesis and it was determined that the mean activation time for at least one of the recipes is different, it would be appropriate to conduct multiple comparisons. And the purpose of that is to determine which recipe activation time differs from the others. We're going to conduct the multiple comparison in a follow-up video.